All right, hey everyone. For those of you who don't know me, I'm Avnish. I'm a huge quantum computing enthusiast, and over the past few months, I've been working on a research project at QWorld with undergrads, master's students, and even postdoc researchers. And what we've been looking into is how quantum computers could be applied to the vehicle routing problem, which is a kind of logistics optimization problem. So let me break that down more. What is the vehicle routing problem all about? Well, let's say you're a delivery company. You've got a depot, a few trucks, and maybe 30 or 40 houses that you have to deliver products to. So you might be UPS delivering packages or Canada Post delivering the mail. Your goal is to find the optimal route for all of these vehicles to deliver products to each of these houses and return back to the depot. And you want to minimize the amount of time that these vehicles spend on the road, because the amount of time they spend on the road is directly correlated with the amount of money you're spending on gas or whatever. So this is sort of a financially motivated problem, and it might not seem like a huge deal, but it's a microcosm for a lot of more important applications in logistics, like food distribution or supply chain management. You know, if you're in any industry that has to move products from one place to another or move raw materials from one place to another, you need to be thinking about vehicle routing. Another important one that's especially become more important recently is vaccine distribution. We want to get vaccines to people as fast as possible and keep the vehicles on the road for the least amount of time. My mentor actually worked on vaccine distribution with quantum computing. So what I'm going to do right now is something that I haven't tried before, which is showing a demo. So I've got my code here. Let's just generate a new vehicle routing problem. So this is it. I've got a few nodes here. I've got 5 nodes, not too many. And what I'm going to do is start at node 0, which is the depot, and try to find a path for 2 vehicles that reaches all of these nodes in the minimum amount of time. So first, we're going to run a classical solver that Google made called Google OR Tools to see what it looks like. So it's kind of hard to tell what the route is, but you can see like a path that the vehicles are taking. And now we're going to run the D-Wave solver, and while we wait for that to run, I'm going to continue on. So how do we actually go about solving these kinds of problems? Well, you can represent each possible set of pathways that a vehicle can take as like a configuration or a sequence of bits. So, for example, 1 bit might be a 1 if vehicle number 5 is at Jerry's house at the 5th step along its route. And you do that for a bunch of different vehicles, a bunch of different time steps, and a bunch of different houses, and you end up with a huge sequence of bits whose configuration corresponds to the paths that the vehicles are taking. And with each configuration, you can associate an energy or a cost. And energy and cost are kind of really related things in quantum mechanics, which is surprising but pretty cool. Basically, this cost or energy represents how long the vehicles are spending on the road in total. So your goal is to find the configuration that minimizes that cost, and that corresponds to your solution. So how do we represent these variables? Well, an intuitive way to think about them is with magnets. So, this is kind of a difficult problem to solve for classical annealing. So the way we do it with classical annealing, which is an interesting classical solving technique, is you start with a random point. So you pick a random configuration, and then you jump to another random configuration and compute the energy for that. And you keep doing this for a bunch of different configurations. But what you do is, as you progress the computation, you reduce the amount of sporadic chaos in your jump. So you start jumping to smaller and smaller increments. And the way you jump is now dependent on which way the gradient moves. So for those of you guys who have done AI, show of hands, how many of you have experience with AIs? Okay, that's what I thought, right? So there's a lot of people here. And you guys are familiar with gradient descent, right? You're trying to move in the direction that minimizes your cost function. So this is the same thing, but we do this probabilistically. So we have a probability of moving back up against the gradient. And the reason we want to do that is sometimes you might be in a local minimum, and moving upward in the opposite direction might get you over the hill to a better solution. So that's where the probability comes in. Now, if you are in a local minimum with a really high energy barrier on both sides, it's very unlikely that you'll be able to cross that energy barrier and get to a better solution. That's the issue with classical annealing. But with quantum annealing, there's this effect called quantum tunneling, which allows us to instantaneously jump across the barrier with some probability without any regard for how high that barrier is. It only depends on the width of that barrier. So that's what gives us hope that quantum annealing might have some benefit. So again, as I said, we can represent each binary configuration or each set of these binary variables as a magnet. And if a magnet is pointed upward, it might be a 0. If it's downward, it's a 1. And these interactions between magnets represent the weights or costs between, or the distance between 2 houses. So if you're at Jerry's house at time step 5 along your route, that might be represented by a magnet oriented upward. And then if you're at Bob's house at the next time step, that might be represented by another magnet oriented upward. And if you know anything about magnets, you know that like poles repel each other. So if you force those like poles to be oriented in the same way, you're creating an energy penalty. And that energy penalty is the exact same thing as the distance between these two nodes. So if both of these variables are 1, you add this cost to the total energy landscape. And you want, again, we're trying to minimize this cost. So another thing that's really important in quantum mechanics is a Hamiltonian. And this Hamiltonian is a measurement operator for which you give it a configuration. So you give it an orientation of a bunch of these magnets, and its job is to calculate the total cost for those magnets. So all the magnets do is represent where each vehicle is at what time, and the Hamiltonian is where you encode the distances between two houses. And that's what tells you how much it costs to go for any configuration or any specific set of routes. And again, your goal is to minimize that. So you start with a configuration, you get an energy out, and you want to update that configuration to get to a better solution. So what we can do with these magnets is sort of directly embed them onto a processing unit. So this is a D-wave quantum processor. Each circle represents a qubit, and these links or edges between these qubits represents a coupler. What this coupler does is it creates entanglement between two qubits to bias them towards a certain configuration. So if two qubits are connected, the coupler can bias them so that they naturally want to be opposite aligned. They naturally want one of them to be 0 and the other one to be 1. Because if both of them are 1, again, we want to insert an energy cost between them. And that corresponds to a vehicle traveling from one place to another, and that costs gas. So that's how we can directly embed this kind of magnet visualization onto a quantum processing unit. And then we tell the quantum computer to solve that Hamiltonian. But first, what we have to do is take any simple Hamiltonian. And this simple Hamiltonian, it wants to put all the qubits in superposition. So that's what we do. We start with all qubits in superposition. And this corresponds to the best solution for this simple Hamiltonian that has nothing to do with our problem. And there's this thing called the adiabatic theorem, which states that if we slowly turn off this simple Hamiltonian and convert it into the complex Hamiltonian that represents our vehicle routing problem, if we do this slowly enough, when we start in the best solution for the simple one, we end up with our goal, the best solution for our complex vehicle routing Hamiltonian. Now, this whole why does it have to be slowly enough thing is pretty interesting. So imagine you have a cup of coffee. Your goal is to get a nice hot cup of coffee on your table. That's not really easy to do. But what is easy to do is get a nice hot cup of coffee in the microwave. So how do you get it from the microwave to your table? Well, if you move too fast, you might spill some of that coffee, and you end up with a less energy favorable state. You don't want that. So it's the same thing here. You can start out with a state that's easy to prepare, a superposition of everything. And you want to find the best solution to your complex Hamiltonian. And if you move too fast enough, you add too much energy to the system. And that energy causes it to jump from this best case scenario to a slightly worse case scenario. And if you add too much, it gets even worse. Even worse. So that's what you're trying to avoid, and that's what adiabatic evolution is all about. Start with a simple Hamiltonian and slowly evolve it into something that you actually care about. So let's just give a quick recap of what we have. We start with the vehicle routing problem. Like a specific city and a specific set of clients that we want to visit. We figure out how to encode this or represent it with these binary magnets and this Hamiltonian that represents the interactions between these magnets. We embed this on the D-wave processor, so we can embed this directly we embed these magnets onto the qubits, and we represent the Hamiltonian with the coupler, the edges, the weights of the couplers between these qubits. And finally, we run this anneal. So we start with a superposition of everything, and we slowly introduce these couplers, we slowly turn them on to create or introduce our problem Hamiltonian. And if we do this slowly enough, we end up in the ground state of our solution, which is, in other words, the exact solution that we want. So, this is the big question about quantum computing. Is it faster than classical computers? And the answer is a definitive maybe. So, quantum annealing specifically, it has a little bit of a rocky history. So, what's up, like this quantum tunneling thing, right? Like it's supposed to be helpful. Remember how I mentioned this quantum tunneling can allow us to cross this energy barrier instantaneously? Well, yes, but you don't often find scenarios where that tunneling comes into play or where that tunneling is beneficial. And it's really hard to see whether tunneling is actually happening. So what some researchers have done is create weird problems that are specifically designed to gain an advantage from tunneling. And that was just for the purpose of comparison. And what they found is that quantum annealers did do better for these weird problems. But you can also simulate quantum tunneling on a classical computer. And if you do that, you get just the same result. So right now, it still doesn't look like there's too much of a benefit yet. But that's not to completely downplay quantum annealing. I mean, D-Wave is a huge company that's specifically been focused on quantum annealing, and they've raised a ton of money for their computers. They've sold them to governments and businesses for like $10 million. So it still is a big deal, but it is an active area of research, and currently we still have a maybe. So what I've been working on right now is trying to get a more definitive answer. So our research group has been looking into vehicle routing and trying to see, can we get some kind of benefit for vehicle routing with these quantum annealers? So that's still an active area of research. Tons of researchers are working on this beyond just vehicle routing to try to figure out if we can turn this maybe into a more definitive answer. I forgot about the demo. I forgot to show you guys that demo. Okay, so let's see what we have. So this is our solution that we got with our Google OR tool solver. So that's a classical solver. And this is what we have with a D-Wave computer. So you can see this green arrow represents the path that one of the vehicles is taking, and this purple one represents the path that the other vehicle is taking. So this is an example of what a solution to a vehicle routing problem might look like. Yeah, that's how it works.